Hello, my name is Lucy Wu, and I'm the chair of the Young Members Presidential Group, a board-level committee of the International Society for Soil Mechanics and Geotechnical Engineering, the ISSMGE. We serve as the nexus of a global network of geoprofessionals to enable the sharing of knowledge and connection between technical societies. And I'm the chair of the Young Members Presidential Group. We've created the Future of Geotechnics committee of the an online event to engage the global community to think about our profession and what it will look like in 40 years. Over the course of 2 days, we will bring top researchers and professionals to talk about the mitigation of climate change, adaptation to climate change, and technology, big data, and AI in geotechnics. We invite you to participate in this exciting opportunity to get involved in some of the most important questions and challenges our society will face in the future.
Climate change is one of the most complex issues that we face today. The increase of carbon emissions in the atmosphere leads to climate change, which impacts infrastructure, food supply, and the ability of the planet to sustain life on long term. However, population growth and economic advancement demands the use of more energy. So we need to find ways to balance the two, decrease carbon emissions, and still meet the new energy needs by creating a circular carbon economy. Our speakers will present us the opportunities that our profession has for contributing towards the mitigation of climate change through CO2 sequestration and renewable energy, while giving their insights on how energy geotech will look like in 40 years from now.
In the last year alone, many of us have been affected by wildfires, droughts, levee failures, landslides, and consequences of sea level rise. The changing climate affects our built environment and is profoundly reshaping many aspects of our lives. In the adaptation to climate change section of the event, we will explore how our profession plays an integral role in developing resilient infrastructure that can adapt to this changing climate. Our speakers will talk about the latest research and the future work needed to build safe and sustainable communities.
Recent advances in technology have shaped all parts of our lives. The question is, how will that impact geotechnical engineering? Will that be transformative or threatening? Will that be something we should embrace or something we should stay away from? In this session, our speakers will demonstrate the state-of-the-art research involving machine learning, artificial intelligence, and big data. Here, we will together imagine the future of geotechnics.
We will face challenges and encounter problems that we may not even be aware of.
Join your fellow geoprofessionals from around the world to discuss the future of our profession.
Hello, everyone. My name is Julia Prodan.
And my name is Marco Tersayol.
And we are YMPG core group members and also your hosts of our event today. We would like to welcome you and thank you for joining. We are a big community gathered today. We have 986 registrations from all over the world, and we are very excited for such a positive response. It is also a sign that we are approaching a topic of big interest. So today we will engage together in interesting discussions, and we will try to imagine how will our profession look like in 40 years from now. The event duration will be 2.5 hours, during which we will have 2 keynote lectures, Q&A sessions, and also several surveys that we have prepared for you. So to start our event, I would like to introduce to you Lucy Wu, the chair of YMPG Young Member Presidential Group of ISSMGE, to say a few words about our initiative, Future of Geotechnics. Lucy?
Thank you, Julia. And thank you everyone for joining us. We have a lot of people on this conference. We're very excited to have you all here. This is more than we ever hoped for. Before we get started, I'd like to share with you our vision for the event and some words from the ISSMGE, the organization behind this. So the purpose of this event is to inspire you to think beyond your own borders, because our actions will contribute to these global issues and challenges. We are all connected. The topics that we have chosen for these events are not your traditional geotechnical topics. We think that our profession is an integral part of the world around us. And to stay relevant, we need to actively engage with other engineering disciplines, the scientific community, urban planners, policymakers. We're here to challenge you to think beyond your own borders, whether it's political, technical, or geographical. These sessions are meant to enable you to continue the conversation with your colleagues and in your communities. This is just the start. The next 40 years will look very different from the past 40 years. The challenges will be different. The skills that we need to solve these problems will be different. So we're here to invite you to help us imagine the future of our profession and what it will look like in 40 years. So please make use of the chat, introduce yourself, engage with your fellow participants. The chat is for you. If you have questions for the panelists, put them in the Q&A. These sessions are being recorded and will be available for viewing for a month after the event. You'll get an email via Eventbrite on how to access the recording. And now we have Professor Manacero, the Vice President of the European region for the ISSMGE, to say a few words about the society.
Hello, everybody. My name is Mario Manacero. I am the Vice President for Europe of ISSMGE, and it's my pleasure, my great pleasure, to welcome all of you to this event. I am very interested and curious about the presentation and the discussion that will follow, so I try to be very synthetic and to present with a short summary the activity of ISSMGE, in particular for someone of you that are not fully aware that about our international society and the related activity and initiatives. The ISSMGE is made up of 90 member society, national society around the world, with over 20,000 individual members. The society's work is done through leadership from the board, the technical committees, the board level committees, all in collaboration, in cooperation with more than 40 corporate associates. The board level committees provide input to the board on the society's goal and priorities. Our technical committee are made up of 2 delegates from each member society, from each national society. All of them offers unlimited corresponding membership to allow more participation in the committee. The flagship event, the most important event that brings our member society together, is the International Conference on Soil Mechanics and Geotechnical Engineering, which is usually held over every 4 years. Our 20 International Conference on Soil Mechanics and Geotechnical Engineering was scheduled from 2021, but now, due to the COVID problems, has been rescheduled as a fully hybrid conference in May 2022. In addition to the main conference, we have a very special Young Engineers Conference where we invite each member society to nominate delegates to attend. In between the international conference, there are 5 regional conferences that are organized by the 6 regions which consist of the international society: North and South America, Europe, Africa, Australasia, and Asia. If the Australian borders reopen in time for the conference, then we will be finally to an end of the COVID pandemic. We hope you will be able to join us in person. ISSMG resources. The ISSMG also offers some resources that aims to promote connectivity and open access. They are basically cultural resources or financial resources. In the first group, we have developed the Virtual University, which is a massive online open course platform where we are continuously updating with seminars, courses, and in the future, there will be the ability to add quizzes and perhaps certification for the successful completion of the courses. The ISSMG Foundation provides travel grants for young professionals to attend conferences. The International Journal of Geoengineering Case History is an online open access journal where we encourage the sharing of data. The GeoWorld is our networking platform that caters to the geoprofessional community. It is where you can find your fellow geoprofessional and interact with all of our committees, technical committees in particular. In recent years, we have also encouraged conference to host a Bright Spark lecture where younger geoengineers gives keynote lectures, important keynote lectures, in particular in occasion of the International Conference for Soil Mechanics and Geotechnical Engineers. That's all. That is the summary of the activity of our international society, and I am really happy to host under the umbrella of the International Society on the behalf of our President, Charles Feng, and I take also this opportunity to thank very much the Young Member Presidential Group and Lucy Hu as chair of this committee for the organization of this event that I think will be successful and in particular also looking at the connection at this moment, we really are confident on a outstanding success of this initiative. Thank you very much for the participation to all of you.
Thank you, Professor Mancero. So the YMPG represents the voice of younger engineers to the ISSMG board. By being invited to the ISSMG board meetings, we have an actual seat at the table where decisions on the objectives, priorities, and goals of the society are being decided. So now please enjoy the event, and I'll pass it back to Marco to introduce our first speaker.
Thank you very much, Lucy. Thank you, Julia and Professor Manacero. I would like to start this part of the event and kick it off with a first survey. The first survey, in this case, will be only 2 questions for everyone to answer. You can go ahead and click on the poll in your Zoom screen. The first questions is going to be about the presence of energy. So the question will be, which energy source do you think will most likely grow the next years? And according to your education of the university, has really prepared you for the challenges of the future? Please go ahead and cast your poll on the link below. The survey is going to be open for a couple of minutes, but the Q&A is going to open for the full event. So after this short survey, let me go ahead and introduce our first speaker. Next slide, please. Our first speaker is Professor Carlos Santamarina, who is Associate Center Director AMPERC and Professor in the Energy Geoengineering Research Group, EGL, in Saudi Arabia, where he focuses on energy and associated environmental implications, including CO2 geological storage, hydrobearing sediments, and geostorage for renewables. His research goal is to reduce energy consumption in the developed world while maintaining quality of life and increase quality of life in developing nations without following the energy demanding approach in the developed world. So today's topic is going to be about the present and the future, and focusing always what will it look like in 40 years. Once again, the survey is still on for a couple more minutes. Professor Carlos, you have the floor. You can start sharing your screen whenever you're ready.
Wonderful. Thank you. Thank you so much. Colleagues and friends from all over the world, this is an amazing exercise and initiative from the young members, and I'm very grateful to all of you for the invitation and for being here today. So let's get started. The topic officially is energy, climate, livability, and to explore the characteristics of geotech in changing times. I have to say that the introductory video was exceptional and is pointing exactly in all the right directions. And the second comment I would like to make is that I will inject few thoughts that go beyond the topic suggested here in the title. But as I was preparing for the presentation and thinking about all of you, I felt compelled to add a few comments along the way. So let's get started. The first part is about what is already going on and where are we coming from, ending with a short personal note. So these are few names in our field. We could have started way before that with the work of Vitruvius and the famous architect in the Roman times, included Leonardo, but let's say that a name that we will all recognize is Coulomb and his studies on friction. In fact, Coulomb was actually working on charges and many other things, but the work on friction was particularly relevant to us. Is later taken on by Terzaghi, Casagrande with all his studies on classification, and Taylor, who is actually creating the basis for critical state soil mechanics. Amazing work by Bierum and Bishop, not only on unsaturated soils, but their paper at the Colorado conference in 1960-61, I guess, on shear strength of soils is just exceptional. And of course, you will all recognize the names of Skempton and Peck. What an amazing past. But times are changing, folks. Look, this is the Google tool to count words, and the peaks for the word soil mechanics took place in the 50s and the 60s, foundation engineering in the 70s and 80s, so did liquefaction. Geoenvironmental engineering really energized our field throughout the late 80s and 90s, and reached a peak probably in the beginning of this century. Now, when we look at the words that are really popping up, are all related to sustainability, climate change, carbon geological storage. The field has changed. In the meantime, we gain inspiration on the past to proceed into the future. For example, Mendeleev knew less than half of the elements that we know today. However, he put all the information that he knew on a card for each element, and he began moving them on a table like we would do trying to assemble a puzzle. And he realized that there were holes that he had to leave for science to fill in the gaps for the following 150 years. We can do the same today. And in fact, it's taking place. This is what Wikipedia has been doing, bringing the whole community together as we are here today to put knowledge together. And think about how much knowledge Netflix and Google and Facebook and Amazon have about each and every one of us. Imagine if we come together as a community from around the world and we put together all the information that we have about soils, information that we have collected throughout the last 100 years, and we can link index properties and engineering properties to provide an AI tool for anybody, anywhere in the middle of Latin America or Africa or in downtown New York City, to come together, to put together the best design properties to fit these nowadays very complex numerical models and simulators. Times are changing also for the laboratory because of so many sensors and the possibility of putting sensors that capture the multiple physics and the thermal and the pore pressure and the chemical besides the mechanical properties that we typically measure. We can actually do probably a very inexpensive nuclear magnetic resonance and monitor both elastic and electromagnetic waves simultaneously with all our mechanical and thermal properties and chemical effects. Think of the power of a cell phone. Today, it is trivial to do the measurement of a specific surface just by colorimetry using a cell phone. This is taking place today, and if we put together all the information that we gather from these simple devices, benchtop, low cost, together with the databases that we have been accumulating, the possibilities for improving engineering design are dramatic. Let me suggest another thought. We have spent the last, in fact, Bishops wrote a famous book on that, the last 60 years, 80 years, trying to design the most pure test with minimal boundary effects, with very well controlled and friction, very well controlled pressure and etc. Now, what about if we design, instead of making such a simple test, and we need to run many of them to calibrate our models, what about if we design a very complex test, complex in the sense that it has very impure boundary conditions, where every point in the test is not just one point on a stress path, but actually every point represents a different stress-strain condition. So we have a field of stress. We couldn't measure all these points and responses everywhere in the past, but now with simple cameras, we can actually track all this information. So instead of running a large number of tests to calibrate a constitutive model, we have the possibility today to run one, but very informative test. What a paradigm shift. Furthermore, because our numerical models are becoming quite powerful, and because some of our systems are very complex, it may be very difficult to run experiments. For example, these are all cases of methane hydrates, something that Dr. Tersariol knows very well. In fact, he tested many of them. It is very difficult to run a good test on methane hydrates because as soon as we take them up into the surface, they will decompose and then completely disaggregate the soil. However, we may be able to run these tests numerically. It's a weird concept, but it is a real possibility and maybe the only one to get reliable material parameters for design. As some of you may know, we've been working on a revised soil classification system, and it is, in fact, built so much on the work of people like Casagrande and others in the last 80 years. But we are really trying to benefit from the knowledge that we have accumulated in the last 80 or 100 years to develop a new classification that will allow us much better clustering and predictive power of soil properties. We recognize what controls the behavior of fine grains and what controls the behavior of coarse grains. By the way, the SIF 200 remains amazing. What an insightful choice. But in the context of the coarse grains, it is all about how much we have of the fines filling the voids and whether the coarse are creating a percolating network, a load-carrying skeleton, or they are floating in the fines. The transition from the top drawing to the bottom drawing is not 50%. So we need to correct for that. And then we use extensive amount of data, and this is the concept that I'm trying to portray. We must use all the physics that we have learned, and we must use the data and combine the two. This is coming out quite a lot in AI-based systems, physics-inspired, data-driven, data-bound. Another paradigm that has been taking place in the last 10 years, or let's say as a rough number, is to work more with the bioactivity in soils, microorganisms that are trapped inside the soil, and I will tell you more in a few minutes about their importance throughout the geological history of the Earth, as well as to get inspired from processes that nature has been improving and enhancing for the last 3.5 billion years by successive trial and error. Folks, just get inspired by how our lungs perform. It is just amazing, or our kidneys as exceptional filters, or arteries as conduction pathways and creating the plumbing inside our bodies, like fractures create the geoplumbing of the subsurface, or AC cyclic fluid flow into our bones that allow us to prevent osteoporosis by exercising. There is so much that we can learn from ants and birds and clams and our own bodies. And we need to benefit from this accumulated knowledge for the last 3.5 billion years, because now we are approaching situations that are going to be very demanding related to environmental adaptation and restoration, and biomediated, bio-inspired processes are already making a mark in the geotechnical field. So a few observations from this first part of part one is that our field has a very rich history, and it has gone through multiple processes of revision. And now it's time to prune. We don't need to be teaching some of the cooking recipes that we saw in the books from the 40s and the 50s. It's time to move on, because we need to prune in order to expand. And we need to expand to address the complexity of the problems that are coming up. There are revolutions taking place, and there are actual paradigm shifts taking place in our field. It's time to explore them and to embrace them, because times are changing. I would like to add a few more slides on this first part, and it will sound quite a deviation from classical geotech, but I find that this is so critical for the young generation. So please walk with me along this path. I explored many years ago, that is like 30 years ago, what was the productivity of civil engineering faculty in research. And look, there was one peak, probably between assistant and associate professor, and then another peak between associate and full professor. These are academicians in the US. And then a significant, let's call it post-peak strength softening. I'm here at 63. I would, according to this curve, I'm dead. You must wonder, do all fields exhibit this increase and subsequent decrease, and what are the reasons for that? And so let's jump into a completely different field. These are movie directors and nominated to the Oscar, and some of them emerge very early on in their 20s, and some of them remain productive until their 70s. But the peak is also taking place somewhere around the 40s, late 40s and early 50s. And so we explore what are the possible reasons for that. One is probably people are getting sick and they're dying. Really, that is not the limiting factor. The curve remains longer than health would suggest, or life expectancy would suggest. Why does it go up? This is like a Proctor curve. There is a reason why it goes up, and there is a reason why it goes down. Why does it go up? Well, because our field is very broad, and we need to learn a lot in order to be creative. And so we need to continue pushing this curve of knowledge up. We need to continue learning and studying throughout our life. We need to maintain our health and also our mental activity. So this curve, like the saturation curve in Proctor, doesn't pull down the creativity curve. But look at the other components that we found. It was so important to have a purpose, to remain focused, determined with persistence, to surround ourselves with a great environment, and to be willing to reinvent ourselves. I can tell you more about this. We actually studied this for quite some time, and you can find videos in the internet, TED Talk related to this. More recently, COVID pushed us to understand one more dimension. We noticed during the quarantines that people were really struggling. And we began exploring the importance of grit and the ability to overcome adversity. And you can look at wonderful examples, the Martin Luther Kings, the Gandhis, the Maya Angelos, the great Olympic athletes, those who started the Me Too movement, the asylum seekers, or Stephen Hawking. These are just a few of the examples of people who exhibited incredible ability to overcome adversity. And so we set ourselves to gather new data to see what was the importance of grit. This is what we had to, what we set ourselves as a goal, to identify what were the parameters that were responsible for success. Was it intellectual capacity, grit, dedication? And by the time we compile all this data, and we asked lots of people to assess others, so the total of more than almost about 300 people have been evaluated here, from PhD students to academicians. By the time we compiled the data and we did the inverse problem of trying to predict an outcome based on the input variables, we concluded that the best predictive equation was that intellectual capacity is important in this area of ours, but most importantly was the combination of dedication and grit. Hard work and persistence, determination. And there are two groups of individuals here that we were able to discern. Some of them under a negative input in their lives. Of course, we all experience it and it puts us down. But some of them were able to recover and actually overshoot, go beyond their previous performance with determination, not to let the negative event put them down. Others experience more negative response to the event, and furthermore, it takes them much longer to recover. I don't know now to what extent this is genetic or to what extent all the psychological factors that come about, but it is so important that to the extent of our abilities, that we respond to negative events with determination, and that we are driven. And we're going to be challenged in the next generation. Your generation is going to be challenged by the environmental situations and the energy situation that is coming up. Your grit and dedication will be critical. Finally, looking back also at my own career and talking to others, I wonder, in the end, it is success or satisfaction. And we have explored the lives of many. And right now, I'm almost ready to conclude that it is not the smartest, nor the grittiest, nor the most successful that is satisfied. Apparently, satisfaction belongs to those who find and embrace their calling. To those of you who are here today, clearly we do have a calling, which is to contribute to society from the perspective of our field. On that note, I understand that the organizers are ready for the second survey.
Thank you, Carlos, for the first part. It has been very, very nice and very, very inspiring. So let me jump for the next slide, please. And that will be the second survey. The second survey, we would like to know from the audience, how much do you think climate change will impact the future of our field? And the second one is, what is the most important tool to face the future challenges also in our field? Please go ahead and click on the poll link below on your Zoom. It is going to be open for a couple of minutes. And as always, the Q&A is going to be open throughout the entire event. So please go ahead and put all your questions to the panelists right there on the link. Carlos, you're ready to go.
Okay, let's give everybody one more minute and I'll continue. Thank you all for your input. It works both ways. It is important for us to have a feeling for how the community feels, but it is also an opportunity for every single one of us to become involved in these challenges. So let me proceed with the second part of this presentation. And so now let me talk a little bit about the future. And let me start by saying that I am a very optimistic person. A very optimistic person because I bet on the intelligence of people here present in the audience and their commitment to addressing the challenges that we are facing. But let me also say that we are facing an unprecedented situation, and it is worldwide. And there are many important changes that are coming up. It is likely that probably traveling as we know it, flying around the world, is not going to be possible within the next generation, not to the extent that we have done it. In fact, right now, flight tickets are increasing very rapidly because of the energy situation. So let's look a little bit more at what is in the news these days. We need to put our fingers in the pulse and feel the pulse of the situation. Let's see some of the news. We have seen plenty of droughts. I saw somebody from Afghanistan, so pleased to see you present in the audience. With so many struggles, including the drought. But the drought has also been in part of the US, in Australia, in Greece, with fires everywhere. The US pulled out of Afghanistan. That was in the news for several weeks with all its implications. COVID has been with us for the last year and a half, and we've been tracking it carefully around the world, and we know pretty much the peaks where they are in different countries of the world. But look, folks, this is the one I just gathered today. There are still 450,000 new infections every day, 500,000 infections every day. And then I have the feeling that the winter will be cold and expensive in Europe. Putin is controlling how much gas is going to release to Europe. And this is already having an impact. Take a look at what is happening in Poland with coal. Look at the climate changes that are taking place worldwide. We're going to be going around the Arctic. There will be times in the Arctic where there will be no ice. Sometimes in the year, the instability of the polar vortex, the cyclones, the flooding, unprecedented flooding in Europe earlier on in the summer. In the meantime, in the news, we saw the new IPCC report. And by the way, please do stay tuned because in less than 1 month, the new UN event in Scotland will take place, COP26. Please follow the news. This is going to be of critical importance. Well, what did the IPCC report, the latest version, say? Well, now we have higher confidence in what is coming up, which means narrower ranges of uncertainty. It is quite clear that humans, we have influenced the climate, we have caused the global warming that we see, that the situation is unprecedented. The current rates are unprecedented within the last 2,000 years. And no doubt that the extremes are now attributed to human influence. What is happening in the future? Temperature will increase by 1.5 to 2 degrees Celsius within this century on average. In some parts of the world, including Saudi Arabia, the temperature may increase significantly more, making livability a major concern for most of the peninsula. There will be increased frequency and intensity of the hot extremes and of the global water cycle because the temperature will be higher in the air. It can carry more moisture, creating more severe floods as well as droughts. The ocean and the land carbon sinks are really getting saturated, so they will become less effective. While we are pumping more CO2 into the atmosphere, the natural cycle will become less effective. And the changes that we're causing today will be reversible for centuries to millennia. While it is unlikely that certain outcomes will occur, they cannot be ruled out. For example, significant alteration of the ocean circulation, which has huge effects on the climate. This is really a just these few statements that I'm highlighting here is really of major concern, and we cannot take any of these lightly. But there are other news, and the courts have now ruled that Shell has to cut emissions, something that now is back into the courts, but this was a major accomplishment. Go back and think of what happened with the, if you remember, otherwise review the news, what happens when the tobacco companies were finally beginning to lose court cases. This may be a tipping point, folks. And coming from Argentina, imagine with all the batteries and all the Tesla taking place, and Argentina has one of the largest lithium mines in the world. This is also going to have implications of political and social relevance. So what about the link between the energy, the climate, and livability? Let's explore some of that. Energy is critical for life. Look, our ability, all the following ones are correlated with power consumption per person. Our ability to access water, life expectancy, infant mortality, schooling, electrification, and income are all intimately related to power consumption. Each point here represents a country in the world. I call your attention to two vertical lines. The first one on the left is at about 0.1 kilowatt per person. That is 100 watt. That is the power consumption by a 100 watt light bulb turned on permanently 24 hours a day. That is our body. That is 2,000 calories per day. Our body is exactly the same as a 100 watt light bulb. And that means that that is the minimum energy that we need to guarantee to have, to be alive. Therefore, you must wonder, how do people, and so many countries, many of them in Africa, how are they surviving with such a low power consumption? And they don't do it very well. Look at infant mortality is huge. Life expectancy is in some countries is less than 50 years of age. On the other hand, we saturate the scale of quality of life at around, let's say, 2 or 3 kilowatts per person. So all the other countries that are to the right, let's say those who are consuming more than 5 kilowatts per person, and we could go even lower, are really over-consuming beyond the needs to achieve top quality of life. And so this is now power consumption versus quality of life for all countries in 2020. And by then we were consuming 18 terawatts of energy. By the 2045, we are anticipating 26 terawatts of energy, which is a huge increase. 7 terawatts would be, the difference here, would be equivalent to 7,000 of the largest power plants that have ever been built, nuclear power plants that have ever been built. 7,000 new power plants in place to accommodate that demand. We have only had 500 nuclear power plants built in the last 60 years, so clearly this is not the solution. But just to put in perspective what this means is huge. But furthermore, if we track every single country, and we did, they are all moving up in quality of life in general, but they're also increasing, they are doing so at the expense of power consumption per capita. This is a very difficult situation to overcome. And so if we're going to be looking into a sustainable energy system, we have to be thinking that the big expenders have to reduce their power consumption. And the countries with low quality of life, we have to help them increase their quality of life without necessarily increasing power consumption. That is critical for a sustainable energy system in global harmony. So how can we, in our field, contribute to that? I'm going to begin moving a little bit faster for the presentation, but let me just add here a couple of things. When you hear a lot about renewables, yes, they are coming up percentage-wise, but look, the absolute consumption of petroleum, gas, and probably coal is going to continue increasing for the foreseeable future to satisfy the demand. One more thing is, if we're going to transition to other energy sources, this requires massive changes in infrastructure and technology, and that requires energy. And right now we depend on fossil fuels, so the transition out of fossil fuels will be fueled by fossil fuels. Significant increases in demand. I just would like to remind you that fossil fuels is accumulated solar energy, and it accumulated thanks to bioactivity. It was captured by photosynthesis, and then it gets trapped underground. So we have 400 million years, all the Jurassic plus, of solar energy trapped in coal, gas, and oil, and we're pulling it out of the ground, starting with the scientific industrial revolution, probably ending within the next 100 years. So the era of fossil fuels is very, very narrow, and we're releasing all that in 300 years. It took 400 million years to accumulate. There's such a mismatch of the time scales. It's scary, isn't it? Furthermore, we're releasing all that CO2 because we pull it out and we burn it. We release it back into the atmosphere, which is a very thin shell, which is responsible for the balance of heat on the Earth. And that is where global warming is taking place. And now, this is the actual measurements, and these are the models. The models and the measurements now are becoming very predictable. They have really improved dramatically, and the situation is quite clear. So we can match the history, and we can predict the future. One more element that I would like to suggest is that we also follow the water. All these problems are highly intertwined and woven together. For example, in Saudi Arabia, we import about the 95% of the food and many other imports. Together with that, you have the embodied energy, the embodied water. To give you an idea, the imports in Saudi Arabia today are about 2 cubic meters of virtual water per person per day. So follow the water. This is the size. Now let's relate the economy to energy and CO2, which will lead us to climate. This is the size of the economy worldwide, $80 trillion. And we consume 160 tera kilowatt hours. And we release 40 tera kilograms of CO2 into the atmosphere. I use these quantities because they allow me to divide everything by 80 tera. And now we can conclude that for every dollar we spend in anything, from a candy to a car, to building a house, to making a major infrastructure development, for every dollar that we spend, we can anticipate that it will involve somewhere in the economy 2 kilowatt hours, and that it will involve the release of 0.5 kilogram of CO2. This is such a powerful relationship that I invite you to please use it to assess the impact of your lives and the impact of engineering choices that we're going to make. If we're going to come up with a new project and we want it to be carbon neutral, the cost of the project has to be such that we are going to compensate for all the CO2 that will imply. Please follow the power because it will help you make important decisions. This is the power flow in the US. And on the left-hand side, you see the contributions of the fossil fuels, which is 83% in the US or about. Very limited components of the other ones. I call your attention to the fact that nuclear is not out of the question. I think that it will be coming back. Otherwise, we don't have a chance to produce more power and capture and retain low CO2 emissions. But I call your attention to the fact that the transportation system is based on petroleum, and it is the most ineffective energy system component in the energy system. Transportation must go through a dramatic revolution. And indeed, governments now are promising major expenditures to improve the economies, and now 3.5 trillion, in fact, is the other one was the emergency, the next one is the plan in the US, $3.5 trillion is taking place these days. Please follow the news. And in India, there are similar promises. Now, the concern is, will this money be used to reinvent the infrastructure or to do more of the same? That means more of the infrastructure that was optimized for cheap oil, which will not be the case anymore. Let's not miss the opportunity to reinvent our engineered infrastructure. For those of you who come from Asia, particularly from China, this is the chart for China, which is completely out of scale. Let me put, for example, wind is only 250 out of 100,000, let's say. So this actually doesn't exist in this chart. So let me put things to scale. China energy is based on coal, which is, as you know, emits twice more per kilowatt hour than gas. And this is the actual chart for China. It takes a long time to analyze all this. It's just magnificent. I invite you to look into it. So now I'm going to end with a few thoughts about our role as a profession. And remember words such as fossil fuels, energy transition, water, climate change, delay or disorderly transition, the issues of food security that we just touched upon. The circular carbon, in other words, this will require that we capture the CO2 before we release it and we inject it underground. The implications on livability. And if we have money, should we just go ahead and buy land where agriculture can be produced? Major issues with land grab around the world. Net zero economy is a dream, but this is a driving dream. The issues with inequality will be exacerbated and the role of renewables. So how will all these events affect our profession, and how can our profession affect the future? This is the reason why we are here all today. And I think I'm just going to present this chart very briefly. This is an analysis of the energy geotechnology field. These are the fossil fuels, oil, gas, and coal. These are the renewables. Geothermal, major role for us. Hydroelectric, wonderful, but it was great in the 40s and the 50s for China at the end of the 20th century. But right now, this is pretty much saturated. Wind with some potential, solar with great potential, particularly for the developing world. I don't think that nuclear is out of the picture, even though Germany and Japan, etc., are committed to walk away from nuclear. I think it will be very difficult to walk away from nuclear. Associated with all this, now we can understand how our field can contribute to the resources, the assessment, the setting of facilities. What can we do with energy storage? What do we do with the waste? Look, CO2 will be injected underground, fly ash. We have repositories around the world and major failures, very, very critical facilities. What are we going to do with low and high nuclear waste? But associated with all this is huge energy demands for minerals. I gave you the example of lithium, but all forms of minerals for this transition in the system. So we have to embrace the challenges of minerals as well. This is 100% our field. Finally, let me say that conservation and efficiency are critical. Let me give you an example of efficiency. Our crushers, the ones that we crush rock to make concrete, our crushers are some of the most inefficient systems. Only 2 or 3% of the energy goes into creating new fractures. The rest is wasted energy. Marco, unless you tell me that I have another 5 minutes, I will expedite the rest of the presentation.
Okay, please go ahead.
5 minutes, okay. So I'm going to give you one example, the case of CO2 geological storage, because we're really counting on it for this circular carbon economy. Let's analyze a little bit what happens. We inject CO2 at high pressure. It gets depressurized as soon as it enters the formation. Because of depressurization of a gas, it means a drop in temperature, which produces freezing near the injection well. It may freeze the water and it may cause some plugging, but then the CO2 has much lower viscosity, let's say supercritical CO2, so it will invade in fingering mode. It is lighter, so eventually floats and gets trapped against the seal rock by capillarity, and also the lateral expansion will also be limited by capillarity. CO2 dissolves in water and acidifies the water. So it will take the water out of equilibrium with the formation, and that means that the minerals will dissolve, both in the storage as well as in the seal rock, in the seal layer. Water will dissolve ions, and dissolved CO2 is heavier than the background water, and so it will begin convecting, sustaining this process. So look at all the things that we're talking about, folks. Freezing, fingering, diffusion, dissolution, advections, convections, mineral dissolution, sediment contraction, probably fracturing. What a complex problem. And so these are some of the ongoing processes, and some of them go back to some of the most basic concepts in our field, like filters. We go back to Terzaghi and the filter criteria. Some of them addresses the issue of crushing that became very popular in the 80s and the 90s. But other ones, multi-phase fluid is a very sophisticated version of unsaturated soil mechanics. We really have to go way beyond that, but we do have the foundations. And so these are all critical phenomena that we need now to begin to understand, advance, and teach. So let me give you an example of dissolution. In the community so far, we understand what happens with hydrochemical coupling. And so depending on what rate it invades and how much diffusion takes place compared to the advection and the dissolution and the chemical reaction, we have different dissolution fronts. But that is true if, for example, in a rock. But what happens in a sediment where the medium is not cemented? So dissolution, let's say, of the red points means that there will be a skeletal compaction and reassessment. Let's take a look at that. And as it is dissolving, you can see the front. It will accelerate in few seconds. Now it's accelerating. You see that the front is moving down because it's dissolving some components and washing them out. But then, under certain conditions, shear bands develop. Very complex. Hydraulic conductivity will kick up, shear deformations, etc. If there is one process, the complementary process will take place somewhere else in the formation, which is precipitation, which can happen in many different forms, and we see it throughout nature. I'm not going to dwell on this anymore. Let me just finalize here saying that repetitive loads are going to gain much more importance in the near future, and they come on all forms, from mechanical to thermal, environmental, of all kinds. And in repetitive loads, we have to have two concerns: how much is going to squeeze and change the volume, but also how much is going to shear. For example, thermal heating of this rock mass will create expansions and contractions and the wedging behind it, which will lead to the final failing of the structure. I mean, imagine this wedge here in Eugenia Canyon, and this wedge will eventually push this rock down through the different cycles, and we have experimentally measured that. So now it's time to close, and I am very much like some of Lucy's words at the beginning. I don't think I'm quoting her, but it's along the same lines. For our field to remain vibrant, we must be relevant. And furthermore, it's our duty, it's our responsibility to society. We must be relevant. And there are infinite number of questions and paths that we can choose in this complex field. So let's make sure that we choose those that are not only fun, it's good to do fun things, but also the ones that are both fun and relevant to society. Sorry, just lost control. So when you follow the news, you realize that change is coming, probably not fast enough, and we may be reaching a tipping point. See what happens in Scotland in 1 month. It will be very important. The problem is it has a tera size. We need to find tera scale solutions. Maybe not one, but in combination, it must be of that magnitude. Follow the money, follow the energy, follow the water. To have a sustainable energy system, we need to stop overconsumption, and we need to improve quality of life in developing nations. Leapfrog technology is critical. Solar will play a critical role in developing nations. For us, for our community, we must contribute. There are great opportunities, but they will always require that we go back to understanding the fundamentals, because it is not building highways. The problems are now distinct. I am very grateful to Julia and to Marco for this opportunity, and to all of you for being here today. Feel free to reach out to me anytime. It will be my honor to chat with all of you. Thank you.
Thank you, Carlos. Has been a very thought-provoking presentation. It's very, very enjoyable to see all your thoughts in only one 50-minute talk. So in order to continue, please stay there, Carlos. We would like to show what is our first surveys, the results. And the first question was, which energy source will most likely grow in the next years? And apparently the audience think the new wind and renewables are coming in. However, you mentioned that nuclear has to be kicking in as well. What do you think is this difference between what the audience think and what is your outcome of this?
No, clearly, wind and renewables will play a critical role, but we are starting from a very small platform, so it still has to grow. But right now, solar there is parity with other expenses. They will grow even faster if we don't use the wrong subsidies. For example, for the oil and coal industry. So we let the market really take place the way it should take, and probably we do charge for CO2 emissions. So it's like garbage collection. We pay for garbage collection. We should be charging for CO2 emission. That will provide a new balance to the energy economy equation, which is critically needed. Nuclear is a bad word. It's a very concerning topic, but Fukushima didn't help. But I think that there are lots of initiatives going on. I have the feeling that nuclear will be part of the mixture more than we think. Oil and gas is also becoming a bad word, but let me tell you, I think that there will be trillions and trillions of dollars in additional expenditure to continue producing oil and gas and in consumption, just because of the huge energy demands worldwide. So I think that reflects what we would like to hear, but the reality is a little bit different.
That's very well put, yeah. With respect to education, one of the questions was, do you feel that your education has prepared you for the challenges of the future? And it's almost the same value. Do you think that our curricula at this point in academia has to be changed in order to address the future, or what we have is enough?
Once again, these are a priori thoughts, but let me share with you a personal experience. My father died at 93. He would be 100 years old today, and so I had a chance to chat with him a few weeks before he passed away. And he asked me, what are you teaching these days? What are people teaching these days in the undergraduate courses? And I mentioned all the things that we were teaching. I said, I learned the same things in 1940. And that thought has remained with me since. Yes, we need to teach the fundamentals. We are going to continue using stress, strain, pore pressure, effective stress, by all means. But I think that we have to get very serious reanalyzing our programs to train the next generations to address the challenges that we are facing. So I would be more on the disagree side.
Well, the audience is 45% agree with you, so that's good. And just because of time, I will jump directly to the second survey, second question. There was, what is the most important tool that we have to face the future challenges of our field? And most of the people, they say that is technology, almost 50%. However, you always mention the fundamental approach has to be the driving horse. Do you also feel that technology is missing, or not?
No, No, I think that this probably would capture my sentiments or the overall distribution. We need to understand the fundamentals to advance, but technology is required. One is the foundation to the other. We need to develop better ways of drilling wells, better ways of sealing wells. And just to give an example, and the possibility of preparing formations to store energy or to store CO2. From fundamentals to technology, they need to come hand in hand to address the situation.
Excellent, excellent. Let me jump to some questions from the audience. Julia, I think you have a couple of questions that you want to start.
Yes, I do have some questions. I will also have to say what an inspiring presentation. Thank you so much, Professor Santamarina. So the first question that I have here is the following. I put it as it is. What is the capacity of our planet to accept CO2 by injection? And how much can we inject in connection with the planet needs? Also, what would you say is the biggest geotechnical challenge in connection with this?
Okay, wonderful question. The capacity to store CO2 is very high. We have the huge repositories with formations filled with brine. We have the possibility of doing mineralization, for example, in basaltic, basic basaltic rocks. So there are a large number of possibilities. Furthermore, CO2 is not the same as nuclear. Nuclear, we do want to store it for 100,000 years or more. And by the way, we don't really know what happened 100,000 years ago. It's kind of challenging to predict what will happen 100,000 years from now. So it is indeed a very critical problem. And so it's not surprising that we do not have a nuclear waste repository yet. Probably one is opening very soon in Finland. Very, very difficult and not to some extent a scary proposition. CO2, on the other hand, I think is going to leak in most cases. This is not an opinion shared by everybody, but I think it's just it's a relatively small molecule that it diffuses very fast and then dissolves a lot in water. I think that we're going to see leaks. We see leaks in the North Sea where they are re-injecting for enhanced oil recovery. The issue is that CO2, if we manage to keep CO2 200 years, 300, 400 years underground, while we go through this phase of fossil fuels, I mean, we're not going to be using fossil fuels in 200 years, right? And so we just need to keep it underground for such a period of time. And then if it begins to leak, nature will be able to take care of it. Right, both onshore and offshore. The problem is in the near future that we are already exacerbating the situation. So it is not so scary from that point of view, and there is plenty of capacity to store.
And what do you think is the biggest geotechnical challenge with regards to this?
Yes, all the coupled processes. And by the way, in our community, we are exceptionally well qualified to address them. Think of people who are doing complex numerical simulators. I know the community in Europe and in the US. The thermo, chemo, hydromechanical coupled processes. We are uniquely qualified to address them, and we should just jump in.
Okay.
The couple processes.
Yeah. So back, as you mentioned, to the fundamentals, but new fundamentals, right?
Indeed. Which means that we need to understand the physics, but also develop the right laboratory protocols and the right calibrations and constitutive models, etc.
Thank you so much. So I will move to the next question, which is, let's say, a bit more general one. And it says, how can geotechnical engineering practices and works lessen the carbon emissions in general while addressing the needs of societies most vulnerable to climate risk?
What a great question. I think that this series of presentations, starting with mine today, but the whole sequence of this series, I think is an invitation for each one of us to think very much in depth as to how can we contribute, right? Some of you will be very creative and will develop new ways of transportation and will get involved in the transportation sector or in retrofitting homes to accommodate the more expensive energy demands. So I don't think that there is a silver bullet here that I will give an answer. I'm just saying within your discipline, get involved, think of that relationship between the economy and energy and emissions of CO2. How can you untangle it and minimize it and contribute responsibly towards engineering solutions? That was a very fuzzy answer, but I really think that we can all be part of it.
Yeah.
Yes.
For sure, it's a very broad topic, and we could, engage in discussions and develop it for hours, because indeed we have some interesting challenges that are waiting for us in the next years in connection with our profession. So thank you very much for your answers. Marco, what about you? Do you have some questions?
I have a couple of questions from the audience. I think we have time at least for one. Abdul would like to ask, what is the prospect of extraction and use of methane hydrate marine sediments in the coming years, given that if released to the atmosphere, it has a devastating greenhouse effect?
Very good question. So let me start by saying that the IPCC report specifically highlighted methane leaks into the atmosphere. Methane is leaking from almost every well and naturally from many parts of from the permafrost to offshore marine deposits, from how do you call it, waste storage facilities around all our cities. We have to stop methane leak. The first thing that I would like to say is an easy hanging fruit. We have to work on that. We have to minimize methane leak. Methane is much worse to climate change than CO2. Please take a look at the IPCC report. And many of us in this community can participate in these solutions. Methane hydrates in particular is a very challenging problem. Methane hydrates are found at water depth greater than 400 meters, typically 700, 800,000, 1,500 meters of water, a few hundred meters beneath the sediment typically, or beneath the permafrost. Methane hydrates form ice, so it's not migrating towards a trap. As soon as the methane reaches the phase transition, the phase boundary, it just freezes and forms this ice. I'm saying this because when oil migrates, it gets trapped in an anticline, and so the only thing that you need to do is to puncture the top and oil will come out. Methane hydrates, you bring a pipe, but it will not dissociate. When you drill a well, it will not converge towards the well, except up to the dissociation front. And so producing methane hydrates is still it's not a well-known, there is no viable economical method yet. But the only thing I can tell you is that there is more carbon trapped in methane hydrates than in coal, oil, and gas together. So many countries like China, India, Japan, even the US are looking at it very seriously. It's not in the near future, and probably it will be good left untapped.
Thank you, Carlos, for your honest opinion. And I think we are almost done with the time for questions. Carlos, please stay online. And if there are more questions in the Q&A, you can go ahead and answer them. Otherwise, we can compile them and send it to you if you're willing to do that. Julia, you can take over for the next part.
Thank you so much, Marco, and thank you again, Professor Santamarina. We are moving forward to our next section of our event, but before I introduce you to our next keynote speaker, we are at the moment where we launch our third survey for today, which will reply to the following questions. What kind of role can geothermal energy play in the mitigation adaptation strategies? And also, as we all know, climate change will affect human lives. Experts says that, and we see it all over these days. So how do you think it is going to influence the profession of geotechnical engineers? So please don't forget to cast your vote in Zoom in the polls area section. And remember that the survey will be on for 10 minutes starting now. Also, please feel free to put your questions inside the Q&A section. And after the next presentation, we will still have another Q&A session where we will engage all together in discussing those questions. So it is time to present our next speaker. And it is my great pleasure to introduce to you Professor Marco Barla. Professor Marco Barla is an associate professor of geotechnical engineering at Politecnico di Torino in Italy, and also the president of LGIP, European Large Geotechnical Institutes Platform. Professor Marco Barla is also the coordinator of the research group active in the field of energy geostructures, laboratory testing on soils and rocks, numerical modeling, tunnel excavation, slope stability monitoring at Politecnico di Torino. He also holds 2 patents, Enertune and geothermal skin, in connection to the topic that he will address today. And he also has more than 20 years experience as a consultant and founder of a private company, a full engineering company in Italy, which is a spin-off of the Politecnico, active in geotechnical engineering. So Professor Marco Barla will address today the topic of energy geostructures and try to imagine together their impact and what impact they can have at a level of city scale in the future, and try to imagine together with you how will geoenergy look like in 40 years from now from the perspective of the topic. So don't forget to answer the questions of the surveys and also put your questions in Q&A section. Until then, Professor Marco Barla, the floor is yours.
Hello, Julia and everybody. Thank you very much. So thank you again. And as was anticipated, in fact, the organizers of this very nice event, thank you very much for inviting me and giving me the opportunity to share a few ideas here. The organizers of this very nice event, let's say they asked us to divide our presentation into two sections. So the first section is going to be related to, yes, energy, geostructures, or let's say geothermal energy in general. And during the second section, we're going to see maybe we're going to pose some queries about our future profession. So as many, we are many around here, and some are young, some less. But maybe we are quite heterogeneous. So I thought we could just have a few words on what geothermal energy is, what an energy geostructure is, before trying to address some ideas related to the works that we've done recently on possible, let's say, strategies at the city scale, as Julia Prodan anticipated. Now, we're talking about the heat that we have from the earth. Okay, so we know that the temperature below the surface increases of a few degrees every 100 meters and so on. So this is what we're talking about. Geothermal energy takes its power. We want to take advantage of this heat, and I like to start with this picture here. I don't know if you have seen this already, probably yes. This is a picture coming from 1904 from Italy. The guy in the picture is Gino Riconti, and he's doing an experiment. His experiment, the outcome of his experiment was to turn on, I think, 5 light bulbs, thanks to using the steam and this engine that you see here on the screen. So basically, people say that this is, let's say, the start of geothermal energy to produce electricity as we know it today. But in fact, we use geothermal energy since a long time ago. I don't know if you traveled into the Mediterranean, for example, but if you had the chance to visit the ancient Greek sites or Roman, well, you would recognize that there is the use of the heat, maybe coming from volcanic areas, for let's say domestic use and heating of the environment. And in this picture here, you have let's say, a puzzle of all the possible uses of energy. Today, we tend to distinguish between shallow geothermal systems, which involve the first, say, 100 meters of ground, and deep geothermal systems, which go deeper into the ground and uses, let's say, the heat to produce electric energy, while shallow geothermal system uses the heat to exchange it and to heat and cool buildings. So from now on, I'm going to talk about, concentrate on shallow geothermal system and not talking about producing electricity. And when we refer to shallow geothermal system, we have let me take the, I'm trying to find, well, the mouse. You should be able to see my mouse, okay? So look at this picture here. This is the ground surface, okay? This is below the ground. And if you are in a country like the country where I am, which means we have cold winter and hot summer, during winter, your temperature will be something like this, the blue line. So it will be 0 or a little bit less than 0 on the surface, and it will go down and say below 8-10 meters, you will have more or less temperature of 14 degrees. In my city is more or less like that, 15 degrees. While in summer, it's the other way around. We will have around 30 degrees on the surface, and you go down and again in the area of 14, 15. What do we see here? Well, here we see that below a certain depth, the temperature is going to remain more or less constant all over the year. Of course, if you go deeper, then the temperature will increase, as we said earlier, and it may become also quite high in some specific areas of the world, like Iceland, Central Italy, or North America, and you can produce electric energy. But here we're not looking at that. We are taking advantage of the fact that the temperature is constant all over the year for some area. And how do we take advantage of this? Well, because it's hotter than ambient temperature in winter, and it's cooler than ground temperature in summer. And so we can, let's say, move heat from the ground to the surface and vice versa. How do we do that? Well, if you have a lot of water available in the ground, aquifers, you can use open systems, and these are but basically you have a well, you collect water, you use it in a heat pump, and then you re-inject water into the aquifer. More recently, let's say, people started to use closed systems, which means that instead of interacting directly with the aquifer, your fluid goes through a pipe and doesn't have a direct connection with the aquifer in terms of exchange of fluid. Now, if we push a little bit farther, the idea of a closed loop system, we come to this. We come to energy geostructures. What are energy geostructures? Well, energy geostructures are, we come really to geotechnical engineering, because these are structures, or better, geostructures, underground structures, that we give them a double role. Well, we know that every time we deal with a structure as being it is a foundation like piles that we see here, or a tunnel lining, or a diaphragm wall, or a retaining wall, we are in contact with the ground. We have an interaction with the ground. That's our key aspect. I mean, the interaction with the ground. And this means that we have an opportunity there, because if we have an interaction with the ground, we can exchange heat with the ground, and we can go beyond what we call the structural role of the geostructure and try to add another role, which is that of heat exchanger. I have a pile there. I can use that pile to exchange the heat and maybe transfer that heat to the buildings on top. So that's the idea of energy geostructures, which is a relatively new technology, but now has some meaning and some applications. You see some data here that we collected a few years ago. They should be updated, but you see that, yeah, we had some increase with time, but maybe not really booming. So not really booming. Increase, we do have applications, but probably not booming. What kind of energy geostructures can we have? Well, in principle, any kind of geostructure. So you see here on the left, piles, energy piles. In the middle, you see diaphragm walls. On the right, you see tunnel linings, segmental linings. I'm going to speak on this latest one because this is where I spent some time in the last, let's say, 10 years. But in principle, any geostructures can be reinvented. I want to use this word that was mentioned by Carlos Santamarina half an hour ago. Can be reinvented to have a double role. Now I want to show you some experiments that we have done in Italy, in my city. Here you have a bird's eye view of the south part of the city where I come from, Torino, in the northwest of Italy, and you can clearly understand that this red line is a metro line. And we are down here in a new section of the metro line, which has been recently built, and we set up an experimental site here. To do what? Well, to test energy geostructures, and particularly to test energy segmental lining and installing pipes into these lining and use the concrete lining of our tunnel to exchange heat with the ground. Well, it was a real experiment on site, just to understand if this could work or not, to quantify. And I'd like to share this video together so that it's easier to see it in the video. So in order to be able to reinvent a geostructure, so this is how we did it, by hand, by adding to the original design of the system, in this case, simply adding some pipes into the steel cage. What you see here are the steel cage of the segments. If you are familiar with tunnel excavation with tunnel boring machine, these are the segments that the tunnel boring machine will install to create the line. As it was an experimental setup, we had a lot of monitoring instruments. Particularly, this is a fiber optics sensor that we are installing at this moment. The people you see working with me here are my former colleague Alice Di Donna and my current colleague Alessandra Insana, who a lot contributed to this project. Now, when you've installed these pipes into the segments, you put them in the mold and you cast concrete into it. And let's say from now on, there is no extra time added to the process. I mean, if you want to do a segment, you do exactly like this. So the extra time added to this process is that of putting the pipes into the steel sets. Why am I saying this? Well, because this will have an impact on the cost. So if the impact on the cost is going to be minimum, then the double roll makes sense, and we have some sort of cost benefit from what we are doing. Now this is when you cast the concrete, then you open the mold and you remove the segment, you check if water can go through, and then we moved all these to the construction site. And at the construction site, I'm skipping a part, at the construction site, the TBM is installing segments into the tunnel. As you see here, again, there's no additional delay in the process, the procedure. Once the segments are on site, what you will need to do later is to connect each segment to one another by adding, you can see it here, by adding the pipe in order to allow for a full circuit to be created. A lot of instruments were installed, and also in heat pump system and a heat exchanger to try to let me skip this, to try to address and quantify what happened. And here are some screenshots of the experiments. You can understand here that this is a thermal image, and you can see that the rings that were thermally activated have a different temperature with respect to the other part of the lining. And if you take a closer look, you can see even the pipes within the lining. So now we have reinvented the tunnel lining, and we may exchange heat with the ground, with the air inside the tunnel, and let's quantify it. So just making a very long story short, but we made a lot of experiments, and this is the result of one. And you can see here with these lines, the red and the blue line, one is the showing the temperature of the fluid going into the segments versus time here, and the temperature coming out of the segments. And basically you have a temperature difference of around 2 degrees Celsius in this experiment. And what is the outcome is that we were more or less able in this specific geological contest to exchange around 1 megawatt every kilometer of tunnel. So this is the quantification. So if you want, the answer to the outcome of this experiment was, well, it makes sense. It makes sense. It's not a nuclear power plant, but there is an advantage that you can get by combining the role of a structure, of a geostructure with a heat exchanger. And so we wanted to try to understand if this could be brought at a city scale. In this picture, you see the city of Torino. And as many big cities, you will have a metro tunnel going below the ground, and maybe this tunnel will go below many buildings for many kilometers. And if you are able to, allow me to make this animation, if you're able to thermally activate the tunnel and to connect it to the buildings on top, and you can do this for many, many kilometers, then basically you can use this tunnel almost as a distribution system and connect the heat you get from the tunnel directly to the building on top. That was the fascinating idea. So we tried to put it in practice, and it occurred that we are currently designing the second line of the metro in Turin. You can see here the blue, the red, and the light blue line. It's around 30 kilometers. Some will be excavated by tunnel boring machines, other with cut and cover technique. This is the group of the designers. So this was a great opportunity to try to study the thermal activation at the scale of the city. And in order to do this, we had to look at details in different areas of the city, how a lot of parameters that would influence the heat exchange look like. For example, here you're looking at groundwater flow direction, water temperatures. You can see that they are not homogeneous in the ground. This is the alignment of the metro, and in some areas the temperatures are higher, in some other areas the temperatures are lower, and all this will affect your behavior. And as was mentioned earlier, to get the answer, to get a prediction of the behavior, we need to run coupled numerical analysis. And this is a topic where Professor Santamarina said this very clearly, is a topic where geotechnical engineers have the knowledge and have the power to go into it. And here you see some simple numerical models of circular tunnel, of cut and cover, with the effect on the temperature, and you can easily see here thermal plumes due to groundwater flow. But all these allow you to quantify the amount of heat that you can exploit. And this is the outcome. So basically, for example, if you look at this as a metro line, each of this section is showing the amount of heat in terms of kilowatts that you can exploit for that specific range. And you can look at it along the 30 kilometers of length, with different in winter, in summer. I mean, you can go into it, and the outcome were these numbers here, which are relevant and interesting. So it might make sense to use it. And how can we use this? Well, it is the last step of the process is that of looking at what do we have on the surface in terms of buildings, of residential areas and things like that. So if you go along your metro line, you have stations, you have shafts, so points where you can get a connection to the surface. And if you look what you have there, you can find one option. You can say, well, I can directly connect my tunnel with the building on top and do a direct exchange of it. This is relevant, is simple idea, but we try to do something more advanced than that. Because in fact, we can also think that the metro line is a distributing system, as we said, and we could think this as a primary ring connected to another ring, which is a low temperature district heating network. And then you may connect directly to the low temperature network, maybe existing buildings in the area. These are typically high temperature users, so you will need a booster to raise up the temperature, or new buildings, which are typically low temperature users, so you can directly exchange the heat with your, and this makes from let's say from a technological point of view and from the system point of view, a much more exciting way of using the heat. And you see here that there's also a backup connection to district heating. So at the end, what is best? Connecting directly to a building or using a district heating? Look, well, if we look here in this example of this part of line, is just a section of 3 kilometers, we ended up that both ideas were relevant. For example, here we have a very big public building, which is a hospital. And so it's one single user, which has a big need, and you can connect it directly. While in other areas, you have developing areas with new buildings. And so there, it makes sense maybe to have district heating, low temperature network. So both ideas are more or less relevant. So I think I'm on time, and I should stop the first section here. The idea was that of sharing together some ideas on the potential use of geothermal energy. I'm talking about shallow geothermal energy, so we're not talking about electricity production, but exchanging of heat. And maybe one of the queries that we're going to address with the survey is if we can open opportunities for district heating, for cooling systems in cities thanks to this. You have my contacts below. Take a note later on if you need this. We can get in contact. So this is the first section, and I asked Julia if she wants to take the floor and introduce the survey before we move ahead.
Yes, so thank you so much for this interesting and captivating presentation. For sure, it opens up our imagination of the potential of this technology, which is directly connected to geotechnical engineering. So we are moving now to our fourth survey of our event, which plans to answer the following questions. Could energy geostructures play a significant role in the city's transformation towards a carbon-free environment? And also the next one, are geotechnical engineers expected in the future to have a more increased role in the energy transition? So please cast your votes in the poll section in Zoom, and remember that the poll will be active for 10 minutes. Also, I have seen that questions are piling up in the Q&A, so please continue mention your questions there, and we will try to address after this next part, we will try to address as many as possible. So thank you so much again, and Marco, the floor is yours.
Okay, so I continue on. And this was the most challenging part of my talk, at least for me. I mean, because in the first part I could share some of the work that we have done, but now the organizer asked me to look on how our profession would look like in 40 years from now. And when I got this query, the first thing I was thinking is, who knows? I mean, how can I know what is going to go on? So I tried to, well, but I had to put some answers together. So I tried to read a bit. And what I ended up at first was this book here, which is, I don't know if you are familiar with, in 1972, a group of scientists wrote a book, which is called The Limits to Growth. And this open, like, let's say, some questions on where were we going, and the scientists here, Renders, in 2012 wrote a new one, let's say an updated one, trying to say what will happen in the next 40 years. So I found it perfectly matching with with the question that was posed to me, and I tried to go into it to see if there was something useful for geotechnical engineers. I have to say that this is around 300 pages, a bit more than that, and of course it's related to what's happening around the world. And if you look for geotechnical engineering inside here, you'll be a little bit disappointed. Maybe around 10 pages can be related to our disciplines, or even more. But I mean, we need to look things into additional details. But one thing we know very clearly, and Professor Santamarina already plotted this graphic a few minutes ago, coming from the IPCC, that the human factors have contributed a lot in the rise of global temperatures. And this is the comparison between simulations and observed behavior. And you see that without humans, we should have not seen this rise in temperature. So this now is quite established, and it's something we will need to consider in the future. But what I wanted to address was our role in this rise of temperature. When I say our role, I'm referring to the construction sector. So I find out this graphics here, where you see the global emissions of greenhouse gases in this circle here, divided by different colors. These ones are the direct emissions, these are the indirect emissions, but we cannot comment all of it. But what I want to draw your attention on is on the 2 points that I have highlighted, because that is where the construction sector is playing a role here. And it's not that small, because if you make 12 plus 7, we are a little less than 20. Of course, there are other actors that are doing worse than us, but we are doing something. Okay, so in other words, I mean, if our impact is around less than 20%, that means that if we improve or change, or I mean, if we do something, we might affect the global this global picture at least by 20%. I mean, we have a role in this as geotechnical engineers, or as, of course, the construction sector is not only for geotechnical engineers, but we are there. As geotechnical engineers, we can improve this section of the overall picture, which is not a minimal section. And so this is something we have to consider when we work, when we study, when we plan and design infrastructure. Look, yesterday I was driving towards my country house, and in the suburbs of the hinterland of the city of Torino, there are a lot of industrial plants, and I ended up in front of this. And I think it's very clear that this is an abandoned industrial estate. It's not that small. It was, I think that around 600 or 700 people worked here till 15, 16 years ago. And now it is clearly bankrupted and completely abandoned. And you know why? Well, I found it interesting to show you this, because in this place, they were doing this. These are the yellow pages. It's in Italian, but you can recognize these are yellow pages or white pages. Maybe the youngest among you have never seen this, but when I was younger, in order to give a phone call to a friend, I took this very thick book and I was looking for the telephone number on it. And we had all the telephone numbers in the city of Torino were in one of these books. Are you using this anymore? Nobody's using this. You can find the information on the internet, even refer to yellow pages are for commercial. You find everything on the internet. You never open a book to search for this. And the result is that these people lost their jobs. These guys were printing these yellow pages for whole Italy, not only for the city of Torino. So they had a lot of jobs. So this is just an example, probably a silly example, to say that things change. Okay, things change. They can change dramatically. My grandmother says they change too fast for an old people. Okay, so things change. And the question is, are we ready for this? And mainly I should say, are you ready? Because maybe I don't know, in 40 years times, I'm not sure I'm gonna still be here, but you will. So are you ready for things that change? That's the point. Now this allow me to, let's say, to pose two different queries. The first of which is this one, and the second will come later. So yes, climate change will affect our lives. How is it going to influence our profession? Let's see if we can. I'm not giving a full answer to this query. Well, I will try to share some ideas. And I took this picture from Julia Prodan, and this picture shows the projected variation of landslide occurrence in Romania between 2021 and 2050. So it says basically, if we look at the red color, where we have the red area, we will have an increase of landslide occurrence over the next 40 years, 30, 40 years. So that's quite, there's a lot of red if we look at this. So it's really related to a change. I mean, we will have more landslide in specific areas where we had less landslide in the past. So we will need to act in this perspective. Look, this is also, similar features are also occurring in the country where I live, and in the Alpine areas. The photo you see here is a photo from the village where I have my mountain house. And I quoted here a sentence from a recent research related to climate change impacting on Alpine areas. And let's read it together. Temperature increases will lead to less snow and snow reliability, thus impacting significantly the winter tourism industry. Well, I bought my mountain house to go skiing, and this says that in the near future, I will have less snow, so that will impact on my leisure, let's say. But more importantly is the second sentence. An increase in extreme weather events will also decrease the attractiveness of alpine resorts and increase the cost of maintaining and protecting infrastructure. Now, if we are not, as geotechnical engineers, involved much in skiing, I mean, or maybe only for leisure, we are involved a lot in the second sentence here. So maintaining and protecting infrastructures, the knowledge in doing that is a basis of geotechnical engineering. And since we are going towards extreme weather events, then this is a topic that is going to increase in the near future. Look, this is still from the mountains, from the Alps. It's in the Aosta Valley, a little bit northwest from where I live. And you might, if you are familiar with mountain environment, you may recognize that this is sort of channel. I think in English the word is galle. I'm not sure the pronunciation is right, but anyhow, it's a sort of channel. And if you're familiar with mountains, you would know that in this, that when in summer, if you have debris flows, or in winter, if you have snow avalanches, then, well, they will go through this channel, this gully. Of course, not 100%, and this doesn't mean that you will not have no avalanches in other areas, but at least this is a place where you know that sooner or later you will have some event. Now, if we go towards extreme weather events, that means that maybe it's going to snow less, but it's going to snow for a shorter period, all in a shorter period of time, and maybe it's going to rain all in a shorter period of time, giving rise to an increase of the numbers of these, let's say, catastrophic events such as debris flows or snow avalanche. This is a picture taken on the same gully, but this is taken from the helicopter, obviously, after a snow avalanche. See that the picture I showed to you before was taken from here, looking up, and now we are up, looking down. Now, you can see here that we have a road, and there is a car. And what about if this car is here when the snow avalanche comes down? Of course, we want to avoid that. We want to protect the infrastructure, as we said earlier. And so I guess that working on things like this, which is this one is a very simple protection means. I mean, we have I don't know, it's a detection line with some pendulums, and when the snow avalanche comes, the pendulum tilts and activates the traffic light to stop the traffic on the road. It's a very simple tool, and people is now working on using more advanced kind of techniques, radar techniques, fiber optic techniques, acoustic emission techniques, and maybe adding something like artificial intelligence or machine learning into this process to make the system to improve connecting data like weather forecasts, meteo information, and things like that. So I think there is some work to do here, and even a simple example like this may work. This is the detection line before, and this is the detection line after the snow avalanche. So there is work to do in this perspective. But if I speak about infrastructure protection, then it comes to my mind in the picture I have here on the screen. This is a bridge viaduct in Genova, in Italy. And you might have heard about this. It collapsed in 2018. It's called, maybe you may heard about Ponte Morandi. You see the picture here when the viaduct collapsed. It did collapse during a heavy storm, But of course, we cannot say that this collapsed because of climate change. However, it collapsed during a heavy storm. But it brings us, at least it brings it to our country, I mean, it opened some eyes in saying, well, what is the situation of the bridges and viaducts in our country? And we went through an extensive process of assessing the conditions of bridges and now also tunnels. But if you live in an old country like mine, so this may not apply to any part of the world, but there are many old countries where you have a lot of infrastructures already there since quite some time. If look at this picture here, this is showing the amount of kilometers of meters of tunnels built along the years in some part of Italy. This is basically, this figure belongs to one of the owner of a section of Italian highways. And you might see that we had some tunnels built in the last, let's say, 10, 15 years, but most of them were built in the 60s and the 70s. In fact, after the Second World War, 15 years later, in Italy, we had what we call the economic boom. And this is when we built most of our infrastructure. And what does this mean? Well, that today, 50, 60, 70 years has gone through, and the situation of these infrastructures are like you see in this picture. They have been subjected to aging, decay, and now this is clearly posing concern on the safety of the users. But you don't have one tunnel in this situation. The owner I was talking about has more than 500 tunnels in this situation at one. Okay, so this is, if you want, an unprecedented challenge for civil and geotechnical engineers, isn't it? Yeah, you can go there and do works to refurbish tunnels. You know, when I studied at the engineering, I learned how to design and build new tunnels, and now I'm working more than on new tunnels. I'm working more on refurbishment and renewal of old tunnels, which is something I never studied when I was at university. And look, here you have examples of ways, of ideas, of let's say reconstructing in completely or partially the lining of these tunnels. And you can do this from the structural point of view, but isn't it an opportunity? Isn't this an opportunity for doing something different? And Professor Santamarina said to reinvent infrastructure. Well, we have the opportunity to also to reinvent existing infrastructure with this kind of challenges. We can think of energy exploitation, like the example that I showed in the first part of the first section of the presentation, but we can go farther than that. We can think of what we say intelligent infrastructures. So we can embed here sensors, new kind of sensors. You know, you talk about structural health monitoring to help us to assess and follow the lifetime of this infrastructure in the future. And what else? I mean, it's there for you to think, what else can we do here to reinvent these kind of infrastructure? So it's not only the new ones, but also the existing ones, which in old countries like mine is probably the where the work will be in the next 20, 30 years. And there we have to put our interest. And I think the geotechnical engineers can do something there. That was the answers to the first query. And here's the second query. Now, the second query is related to geothermal energy. So I go back to the topic we anticipated in the first section of my talk. So can we use this? Can this play a role somehow in future strategies? Now, going back to this book, I found a sentence here talking about renewables. Initially, the main component of renewables will be solar and wind, And this is in agreement with what Professor Santamarina was saying. After 2025 or 2030, solar energy will take the lead and become the primary source of energy. This is what the book says. Now, if I look on the website, you find that today, yeah, in fact, in terms of renewables, solar and wind have the most. Geothermal energy is somewhere there. You can barely see it. And if I look at the chart in the book, I see this, which is slightly different from the one that Professor Santamarina showed earlier, but his one stopped here, so maybe he was in this area, and if you add 10 years, things may change, but this book says that renewables will take the lead around 2052, will take the lead, and they say that this is going to be almost all solar. Do we agree on this? Look, I personally disagree. I disagree. Maybe they're right. It's gonna be all solar in terms of renewables. But if I can think of what would be the right thing to do, I would say that I would prefer to bet not only on one technology, but on many of them. It's like when you do a diet and they tell you, well, you should not eat only meat, you should not eat only vegetables, you should not eat only fruit, you should not eat only cheese, you should eat a little bit of this, and that. And I think it applies here as well. Solar is probably going to be the key player among the renewables, but what about silicon? What about all the minerals, as was anticipated, that we need to do to go into this direction? So, in my personal opinion, it is good that we, distinguish among different renewables. And by saying this, of course, I'm also saying that geothermal energy can do something. So I read another quotation from the book. It says, megalopolis will be the physical and social environment for the majority of the human beings by 2052. So we will all live in cities, even more than today, this says. So if I combine this, renewables and cities, I end up by looking at what can we do in a city with geothermal energy. And this is an example from London, from our colleagues, Zhang and Kenichi Soga and others, where they said, okay, let's take the city of Westminster and let's imagine that we take every building, and around the building, so in a free area on the streets, not below the building which is already existing, but in the free areas in the streets, we create borehole heat exchangers all around. And if we imagine that we are able to do that for all the city of Westminster, what are we going to gain? Well, and the picture here shows the ratio of capacity to demand of this, and it's clearly we have a lot of green here, which means that there is a lot of potential. Even if we do, if you want, it's a simple exercise, okay? But it demonstrates that there is a lot of potential there. We did something similar in Torino by looking at the situation of, this is the central district of the city. We looked at groundwater flow, temperatures in the ground, but not natural temperatures, but real temperatures. You see here that you have these different changes in color, because this means that maybe someone is already using the heat there because there are already some geothermal installations. And by combining this, we try to do what you saw earlier. So to address what kind of heating potential we could get around the city. And you see that you have some areas where you have high potential, some other areas where you have less potential. So it changes from area to area. What are we looking at here? We're looking at geothermal energy in general. So borehole heat exchanger, energy geostructures, maybe also metro 2 coming down like this. Okay, everything together. And we tried to compute it as well as for Westminster. And our outcome was this figure here, that 57% of the volume of the buildings, can be heated by geothermal energy. It's not 100%, but it's more than half. So this takes me to the end, and by looking at these examples, why shouldn't we give geothermal energy a chance? I mean, why shouldn't we have this as one of the possible renewables within the full picture? In trying to address the query on how our profession will look like, of course, I just looked at a section of it, and you see, I tried to say, well, we will have more extreme weather events, so I expect that we need to work on mitigation and protection. I do expect that. I think we have to improve our knowledge in this area, but we have the skills. Geotechnical engineers have the skills, and I liked this word here that I already underlined it, and then I heard Carlos Santamarina saying it as well. We need to renew and reinvent infrastructures, and we refer to new design infrastructure, but also on existing infrastructure. I want to stress you on this. I think that this is a really an open path for young geotechnical engineers. I think I should stop here and let's open the floor to Julia Prodan to see if we have any comment on the survey.
Thank you so much. So many interesting things to foresee for the future. I really like, and I think it's excellently put, the way you said it, to let geothermal energy play its role. As we could clearly understand from your presentation and from the data that you provided, very accurate, the fact that geothermal energy has such a high potential. And us geotechnical engineers, in connection to this field, we have so many challenges ahead, and it could really have an impact in the energy transition. So talking about the energy transition and the impact, we can look at the results of our surveys, and I will start with survey number 3. What kind of role can geothermal energy play in the mitigation adaptation strategies? We can see from the answers that 54% agree that geothermal energy will have a major role, and 41% that it will have a limited role. So combining the two, I think it's quite clear that we are expecting this to have an increased impact in the future. How do you see, Marco, the results of the first question?
I was reading. I would say that major, limited. Maybe the answer is in between, because in fact, as I said, you should not eat only fruit or only vegetable, only meat. It's a joke, of course. Yeah. But I also saw in one of the queries someone was asking about tropical countries, and maybe I raised this query here because it helped me to answer to this. Of course, it might not be the solution for any situation around the world, but the world is big. We have different climates, different regions. Climates is even changing. So we should find many solutions and add them together. So in some areas, solar will be the best opportunity. In some other areas, maybe we can take advantage of this. Of course, I live in the part of the world which nowadays is relatively convenient for geothermal energy, because we have a hot summer and a cold winter, so we can use it all year round if you want. But this is not the case for all the world. I perfectly understand. So that's why I think that probably it is correct that we see 54% and 41%, because it's in the middle. Probably, if we want to find the right answer, let's say, the right answer is probably there in the middle.
Yeah, and also I think you have pointed out very well the fact that one renewable does not exclude the other. It's also about integration of the renewables in the future and what we should expect.
For sure.
Yeah, go ahead, please.
No, this is something that I was there to, we probably discussed this already, to add it to the presentation, but then it became a bit long. integration among renewables, that's something very interesting. You know, with when you collect heat from solar panels, when I was reading these books, I found a book from the Swedish, the Royal Academy of Sweden, related. The title is "Going Underground," and it was all the opportunities of going underground. And there was one example. This is 50 years ago, something like that. There was one example of collecting heat from, so I'm saying something about 50 years ago, collecting heat from solar panels and heating, in that case, it was water into an underground tank to be used in winter. Well, now we can do that also without using a tank with water, but directly using the ground as, in some specific situations, of course, as how can I call it, a heat storage environment. So I think there are lots of opportunities there with the interaction among renewables, and geotechnical engineers have to take the lead and try to find out where to go in this perspective.
Yes, thank you so much. So looking at the second question of the survey, I think it's quite an interesting result of the survey. We can see that us as geotechnical engineers, we can expect to dedicate ourselves in the future more to the mitigation activities, as well as quite a good balance, I would say, between the answer, between the first two options, and also more increased activity we are to expect in relation to natural disasters.
Yeah, and maybe the most important one is that no one said that is not going to influence our profession. So, I mean, no one, just a few.
Yeah, 2%.
But that means that we have all the clear understanding that, as I wrote, things are changing, and in some way we need to go behind this. And maybe I believe that our role is more on mitigation and adaptation strategies, more in put there than really into natural disasters, where there are also, let's say, other professions that I'm not saying that geotechnical engineers do not have their role there, but other professions probably take the lead there, while we are more on the design stage, on the design side, okay, and on the prevention of the disasters. So that's why we say mitigation and adaptation. So we want to prevent this, to avoid it, or to control it, to govern, to manage. I think that is more our role, and we have the knowledge for that. At least we should try to continue increase to have the knowledge for it.
Yes, so I have to say, looking at our fourth survey, I cannot say I do not agree with the answers, but I have to say, for me at least, it's a bit unexpected, this high percentage for both of the questions. Could energy geostructures play a significant role in the city's transformation to a carbon-free environment? So we have 76% that agrees with this, along with the fact that geotechnical engineers will have a more increased role in the energy transition sector. So what's your opinion on this?
Maybe we can read this as the willingness of people answering to the survey to take part to this change we need in doing things as human beings. So maybe we see this as a way of bringing our contribution, okay, to let's say to the fight that human beings have to go through in the next years, bringing our contribution as geotechnical engineers. So we can maybe we identify the fact that geostructures belong to us, in the sense that we have the knowledge. It's our we studied that, we know how to build, to design a foundation or a tunnel lining. So that's in our hands. So we know how to do it. And so probably that's why not using this knowledge to bring a contribution to the change we need. I can read it in this way.
Yes, I completely agree in the sense that we know that the designing of energy geostructures requires an integrated way of looking at the things from both energy point of view and also mechanical and structural point of view. Okay, so I think we can move to the questions. So we had a lot of questions from the audience. So Marco.
Thank you, Julia. Yes, we have plenty of questions from the audience. Let me start with some of them that seems to be repetitive. So I will choose only one, but that also represents many others. The question from Joseph said, will cyclic temperatures variations exert thermal expansion and contraction loads and stresses on the wall? And I will add to that, what will happen with the soil that is also experiencing difference in temperatures as well?
So I guess the query is related to, let's say, energy geostructures in general.
Correct.
And but to give a general answer is not that fair, because the situation may vary in an important way as a function of site conditions and as a function of the kind of geostructure we are looking at. So yes, it is a topic. It is a topic that a lot of people are studying. So you can find a lot of papers on this, a lot of contribution by elder and younger researchers. So it's a topic I would say we, because I'm among the ones that are dealing with this. However, we should not be afraid of it. I mean, we have to. I think that again, we can say, as geotechnical engineers, as we have the ability, the capability of running, as was anticipated earlier, coupled numerical analysis by knowing how to develop constitutive modeling and appropriate constitutive modeling to track the behavior of soils, even in changing temperatures, in cyclic change of temperatures. Like energy geostructure is going to go up and down every year. And so we have the knowledge to try to address this kind of topics. If we see what people already did, and a lot of works came out that there are no, this is not frightening. I mean, it's something that is under control, let's say. Okay, I don't know if it's a too simplistic answer, but I guess it's the answer.
Thank you for the answer. I do have one more question. If you have all these geostructures filled with pipes, will that have an impact on weakening of the structure or not?
Yes, this is very well connected to the previous query. I mean, we can have a change in the behavior of the ground or a change in the behavior of the structural element, and one influence the other one. So the whole picture is, I mean, everything goes into the same picture. I can answer with related to the experience that I had on mainly on diaphragm walls and tunnel linings, where we have computed and experimented that these kind of changes are not significant to affect the, and not even to change the designs. I mean, just to let me make an easy example. If you design a tunnel lining, you want to know the thickness of the lining. And then we said, okay, but if I put the pipes into it, should I change the thickness of that lining? Well, we made a lot of verifications, and the end up was that we didn't need to change the thickness of the lining. Okay. Yeah, of course, if you look at the number you get from your computer, you will have a 0.01 or something which is additional. But from the practical point of view, there was no need to change based on the experience I had. But of course, this is something we can deal with. We can compute, we can understand, we can try to predict and also find an answer to. It's a problem, but we can manage it.
Excellent. I do have one extra question from Emil. The question is, with the local increase in temperature in the soil cause biological impacts for microorganisms that are affected by the change in heat? Does the heat exchange with the groundwater have a negative effect of such? Do you have any comments on this?
I'm not sure I fully got the query because the audio stopped for a second. So we mean if we will any effect on the
what is the effect of
on the aquifer, on the temperature of the aquifer. So if we talk about the aquifer, for example, we have to look this and take it into very careful consideration, because my presentation was on a city scale. So let's remain on the city scale. If you look at the city scale, you will have many installations. Imagine if we apply what the idea from the city of Westminster to have all those borehole heat exchangers. They will interact a lot among them. So again, there might be a problem of interaction. There might be the situation where one installation will affect another installation, so the second one will produce less heat than the design values. But this is something we can cope with. It can also go the other way around. You may produce more because you have a heater upstream. And so that's why in my slides, I wrote the word optimization, because if we do it in an intelligent way, we might optimize the distribution of this at a city scale, for example.
Thank you very much for the answer. At this point, I think we're almost running out of time. I would like to invite Professor Carlos Santamarina to join us for a general comments at the end. Let me ask you one question to both of you that I believe that you have somehow answered. It would also give you the opportunity to expand if you have any other thoughts that you want to share. And the question is coming from the audience. It says, how may geotechnical engineers make climate change an added value to the geotechnical firm? Do you have any comments that we'd like to share?
Another value on the geotechnical?
Exactly. What I understand from the question is, if you are working on climate change, what it will be the direct impact on geotechnical firms, and how you can actually use that in order to hire, for example?
Carlos, you want me to start?
Of course.
Okay. Well, but you answered to it earlier. You said that geotechnical engineers, I mean, some of us has the knowledge on doing a couplet analysis, and so if the change that we are experiencing will lead us to have more cyclic problems, cyclic in general. It could be stresses that cycles, that can be temperatures that cycles, and so on. Then that's where, I don't know if this is the answer, but that's where our knowledge, our basis, okay, that we learn at university can play a role. That's one aspect, of course. During our presentations, I think that we try to show some other potentials here and there.
So let me jump in. I think that various companies are going to begin finding opportunities related to this. The same as geotechnical companies found opportunities in the environmental period of the 80s and the 90s. In fact, many of them actually even changed their names to adjust. The journal changed the name to adjust to the new challenges and opportunities. The same is going to happen here. If you are near the ocean, you're going to have problems with sea level rise and coastal erosion and saltwater intrusion. If you are next to Marcos' country house, you may have problems with slope instability taking place. And so in the different locations, there will be different geotechnical needs. And the companies that are able to anticipate those are going to be well positioned to capture that slice of the market.
Excellent, excellent. Julia, would you like to jump in? I think we lost your audio, Julia.
Yes, can you hear me now? Yeah, sorry. Okay, so yes, I was saying that we definitely had some very interesting discussions, in our case, afternoon, for others might be morning. And we are very close to the end of our event. And I will have to pass the floor to Marco for the closing final thoughts, but not before thanking everyone for participating, and also our speakers and their very interesting presentations. And you, Marco, of course. Thank you for helping me and joining me. It was a pleasure. So Marco, the floor is yours.
Okay, thank you. Lucy, can you please show the last slide? Okay, well, thank you everyone for attending, all the audience, particularly to our speakers, Professor Santamarina, Professor Barla, Professor Manacero, the support of YMPG Liaisons, the ISSMGE Time Capsule Project and the board, all the media and production that we had in the last year in order to prepare Disaster Film, Piña Colada, ArgoE.com. And please, for the whole audience and everyone who would like to join, stay tuned. We have 2 more events coming up. The next one is going to be in about less than 5 hours, which is adaptation to climate change, about midnight here in Central Europe. And the next one will be tomorrow at 11 a.m. in Central Europe, about technology, AI, and big data. Thank you once again, everyone, and I hope you have a great day.
Thank you.